Let's get started on part 4 of chapter 10. In this section we will talk about IPv6. Let's first discuss the limitations of IP version 4. IP version 4 has a 32-bit address space, so the maximum number of IP addresses that are possible is 2 to the 32nd, which is 4 billion. We have a total of 4 billion potential IP addresses. The population of the planet is 6.5 billion, and many people use multiple IP addresses, so the statement of the problem is we are running out of IP addresses. Two potential solutions, NAT and private IP addressing, which we discussed in the previous section, and IP version 6. So let's look at IP version 6. Whereas IPv4 has a 32-bit address space, IPv6 has a 128-bit address space, 128 bits with which to assign an IP address. If we take 2 to the 128th, we see that gives us 360 trillion potential IP addresses. So that's enough IP addresses that we could have an IP address for every cell in the body of every person on the face of the planet. The big advantage of IPv6 is it gives us many more IP addresses. Now the tricky part is that it is written in a hexadecimal format. This is the IP address for an IPv6 computer, and it looks kind of login painful because it's written in hexadecimal. In hexadecimal, 1 is equal to 1 and 9 is equal to 9. But in hexadecimal, A is equal to 10, B is equal to 11, C is equal to 12, and F is equal to 15. Why do they do it that way? The reason they do it that way is because larger values can be represented with a lower number of characters. So if we look at this IP address format, it looks pretty long and painful, but if we look a little more carefully, we can see this is the network ID and this is the host ID. Now F is represents 15 and A represents 10. So this means this is network 15 and workstation 10. Now, if you have a long string of zeros here, that long string of zeros can be represented by a double colon. And furthermore, if we drop the leading zeros, we now see that this IP address can be represented as F double colon A, network 15, workstation 10. An IPv6 subnet mask is a 64-bit subnet mask. So let's manually assign an IPv6 address to a workstation. Let's assign IP address 2001 colon 1001 double colon 1009 to this workstation. It's done the same way you would assign IPv4 addresses. You click on Start, and then you go to Control Panel and select Network and Internet, followed by the Network and Sharing Center, and you select Change Adapter Settings, and you right-click on your Ethernet adapter and select Properties. And here we can see Internet Protocol version 6, TCP/IP v6. If we click on Properties, you can see that here is where we type in the IP address. So we type in the IP address. I know it's kind of long. Subnet mask is 64 bits, and notice the default gateway has the same network ID as our IP address, and it ends with a .1. DNS we will discuss later in the class. To test TCP/IP version 6 on this workstation, we use the ipconfig command. If I type ipconfig and press the enter key, I can see that the IPv6 address that I assigned to this workstation is 2001 colon 1001 double colon 1009. If I use the ping command, I can ping myself, or if I want to ping the DNS server, I can type ping followed by the IP address of the DNS server. If I can ping the DNS server, then I know that that server is up and running and I can communicate it. So you can see that ping and ipconfig work the same way in IP version 4 and in IP version 6. IPv6 uses a 128-bit address space, which gives us a much larger number of IP addresses. It's notated in hexadecimal, and it can be tested with ping and ipconfig. Let's look at some slightly more advanced IPv6 topics, particularly the address types. A packet header contains the IP address of the destination computer. And a packet might just go to one computer, or that packet might go to many computers. If we go to Microsoft TechNet, we can see that IPv6 has three types of addresses: Unicast address, Multicast address, and Anycast. Let's look at those three. Unicast, uni means one. It's the most common of all, and it's a packet which is only addressed to one other host computer. Multicast is delivered to a group of computers, such as a broadcast to all computers on the local subnet, such as a message that tells everybody the server is going to go down in 5 minutes. And then an Anycast is a packet which is sent to all computers on the subnet, but only one computer responds, and the example would be a DHCP request. Now let's look at IPv6 address scopes. If we go to Microsoft TechNet, we can see there is a link local and there is a global scope. So let's look at those. A global unicast IPv6 address is just an IP address which is assigned to one single computer. A global unicast address is simply an IPv6 address which is assigned to one computer. And we've already done it. There's the example. We assign the IP address to one single computer. Let's look at the structure of the global unicast address. That is to say, the structure of the IPv6 address in the packet header. Now, the original format, which is no longer used, divided the global unicast address into 6 fields. Fortunately, they have since simplified to that, such that the current format is divided into 3 separate fields: global routing prefix, subnet ID, and interface ID. The global routing prefix would be the number which is assigned to the institution overall, CCBC. The subnet ID would be assigned to an individual campus, or maybe just to one building, such as the library. And the last 64 bits of the IPv6 packet header are assigned to the workstation, the host ID. Now let's look at what's called a link local IPv6 address. To understand link local, we have to do a bit of review of DHCP. Well, as you know, with DHCP, a DHCP server issues IP addresses to a DHCP client, and it's nearly identical to IPv4. An IPv6 workstation powers up, it sends a request to the DHCP server, and the DHCP server issues an IPv6 address to the individual workstation. But what if that DHCP server is unavailable? What if it goes down? Well, similar to IPv4, if the client cannot hit a DHCP server, then what it does is it auto-generates its own temporary IP address, and this is called a link local IPv6 address. If we go to the command prompt and type ipconfig and press the enter key, we can see that the link local IPv6 address begins with FE80. A link local IPv6 address begins with F80. So if a DHCP client cannot hit a DHCP server using IPv6, then the computer generates its own IP address, and if that IP address starts out with FE0, then you know it is a link local IPv6 address. Now let's look at planning for an IP transmission, either implementing IPv6 in your organization or integrating IPv6 with your current IPv4 infrastructure. First, let's discuss what they mean by dual stack IP implementation. What we have here is one server has IPv6 and another server has IPv4. So what do we do to allow this workstation to communicate with both? We implement what is called a dual stack IP implementation. That is where we install both IPv4 and IPv6 on this workstation so it can communicate with IPv6 servers and IPv4 servers. If we look at the TCP/IP properties, we can see that IPv6 and IPv4 are installed on this computer. So that means this computer can communicate with both IPv6 and IPv4 computers. They call this a dual stack implementation. Now let's discuss tunneling. The situation is we have one site which uses IPv6 and we have another site which uses IP6, but the link that connects them uses IPv4. And the solution to this is tunneling. Tunneling is where we have an IPv6 network and an IPv6 network, but they are connected with an IPv4 network. So the way this works in tunneling is that IPv4 packets are carried over an IPv4 network and they're delivered to the IPv6 network on the other side. There are three tunneling protocols, Teredo, 6-4, and ISATAP. Teredo is an older tunneling protocol and it's compatible with NAT and private IP addressing. 6-4 translates IPv4 addresses into IPv6 addresses, and ISATAP, the inter-site automatic tunneling addressing protocol, is the newest tunneling protocol, and it's the preferred tunneling protocol, and it encapsulates IPv6 packets in IPv4 packets and sends them over the network. Tunneling carries IPv6 packets over an IPv4 network. Chapter 10, Summary. In this chapter we looked at TCP/IP, the protocol that allows computers to communicate. We looked at IP addressing and testing TCP/IP. We did a review of binary math and looked at subnetting. We looked at private IP addressing, the dynamic host configuration protocol, automatic private IP addressing, IPv6, and transitioning to IPv6. And this concludes Chapter 5. Thank you very much, and have a nice day.